Vertical forces. We're going to be able to describe the interaction of objects in the vertical plane and describe the force exerted on an object by an ideal spring. First, some vocabulary. An ideal string is a string, rope, or chain that has negligible mass and does not stress when under tension. An ideal pulley is a pulley that has negligible mass and rotates about an axle through its center of mass with negligible friction. And an ideal or Hookean spring is a spring with negligible mass and exerts a force that is proportional to the change in its length as measured from its relaxed length. First up, tension. Tension is a macroscopic net result of forces in the microscopic level within a segment of string, cable, chain, or similar system that are exerted on each other in response to an external force. So when you pull on a rope, there are atoms within that rope interacting with each other to produce this overall tension. Tension will always pull. You cannot push with a string. If one of those objects is ideal, the tension within the string is the same at all points within that object. If a string, chain, cable, or rope is not ideal, you have to analyze forces at different points. So what that looks like is if we have a hanging string, we'll give it 3 points to look at. We'll call this point A, point B, and point C. For point A, we have just this small little mass of the string hanging down. So we'll call that mg. It's in equilibrium. It's not moving, so that means the tension at point A is that big. Move up to point B. Point B, now we have more rope hanging down, which means we have more weight. And of course we're in equilibrium, so that means we have more tension. At point C, we have all of the mass for the entire rope, so that's much longer, mg, and of course an equally longer tension. Stuck. Onto the Atwood's machine. George Atwood, English physicist, was most known for his work with an apparatus now named the Atwood's machine, which consisted of 2 different masses attached to a massless string wrapped around a frictionless pulley. A pulley is a simple machine that can make doing things easier. They provide a mechanical advantage. The more pulleys you have, the easier it is to lift something. More pulleys mean more mechanical advantage. Look for pulley systems next time you're lifting weights. We can solve these types of problems using our force problem strategy. First of all, identify there are forces acting on the object. Next, draw a free body diagram for each object in the system, and then create a Newton's second law equation for each object. Solve for whatever we need. So let's practice. Derive a mathematical expression for the acceleration of a system in terms of m1, m2, and physical constants. So I'm going to start by drawing my forces because I realize that mass means there's probably a weight involved, so that's going to be m1g. Then I also have a tension going upwards on mass 1. For mass 2, I have a much larger weight force, m2g minus ft. If this rope is frictionless, as we hope it is, then my tensions here are the same tension. Same magnitude. The directions might be a little bit different, but the magnitude is the same. So let's look at mass 1g. We have 2 objects, so we should have 2 free body diagrams, which we do, and then after we have a free body diagram, we should have a Newton's second law equation. My net force on the first object, stuff that makes it go, is going to be my tension minus the stuff holding it back is m1g equals m1 times a. For my second object, stuff that makes it go is going to be m2g minus the stuff holding it back, ft, same tension, equals m2a. also the same acceleration, because mass 1 is going to ascend at the same rate mass 2 descends. So I can't just solve this equation for acceleration because I don't know what tension is, and tension is not allowed in the problem. It says m1, m2, and physical constants. Physical constant would be like g, not force, not some tension force. So I can't just plug in the first equation. I run into the same problem with the second equation. I can't just divide by m2 because that's still going to leave me a tension in the answer. So instead what I'm going to do, because I have two unknowns and there are two equations and those unknowns show up in both equations, I can just treat this like a system of equations. When I do that, I'll combine like terms. I have a positive tension and a negative tension, so that will cancel out. And what I'm left over with is, let's see here, m2g minus m1g equals m1a plus m2a. I can factor out an a, m1 plus m2 equals m2. Oh, I can factor out a g over here. G times m2 minus m1. And then I'll divide by m1 plus m2 on each side to get my acceleration. Here's my acceleration solved. Let's check to make sure I'm in the right terms. m1, m2, and g. G is a physical constant. So now there's my answer. I'm done. If I were then asked to derive an expression for tension, I can take this acceleration and plug it into any one of these equations and then solve for tension. What do you know? Derive a mathematical expression for the tension in the rope in terms of m1, m2. So I'm not going to go through the entire process, but we started with Ft minus m1g equals m1 times all of that junk that my a was, g times m2 minus m1 divided by m1 plus m2. I can add my m1g to each side. And when I do that, I get my tension. Tension turns out to be Ft equals m1 times g times m2 minus m1 divided by m1 plus m2 plus m1g. From here I can analyze the relationship of what happens if I increase mass 1, what happens if mass 1 is larger than mass 2, what happens if I make mass 2 equal to mass 1. You can do all sorts of analysis from this equation now and make predictions about what will happen. Hooke's law. Consider a mass on a spring. Here's our mass, here's my nice spring. There's my x equals 0 equilibrium point. I'm going to just go ahead and draw a free body diagram because instantly I already know spring, there's an elastic force that's going to show up, and then there's a mass, so there's a weight. Stuff that makes it go minus stuff holding it back is my weight force minus my spring force equals mass times acceleration. My spring force equation, recall, is equal to negative k times x, where Fs is the elastic force measured in newtons. K is my spring constant for the spring. That is the springiness of the spring, or the stiffness. The higher the number, the stronger or stiffer the spring. That also is only constant for a specific spring. If you change the spring, you are also likely changing the spring constant. So that's why I put constant in quotation marks. It's only constant for an individual spring. X is the displacement of the spring. Note the negative in the equation because the direction is always pointed back towards the rest length of the spring. So if I stretch out the spring, pull down the spring, my spring force will be directed back upwards. If I condense the spring, then my spring force will be downwards. This is called Hooke's law, and is named after Robert Hooke, is only applicable if a spring is Hookean. That is, the displacement of the spring is directly proportional to the force the spring exerts directed back towards the equilibrium point, as shown in the equation. Here's something for fun. What quantities from that equation, or the situation, could be graphed to produce a straight line that is equal in magnitude to the spring constant? So that means, given a graph, what am I putting on my y-axis, what am I putting on my x-axis, to get a slope that is equal to k. Right? Nice and easy. That's Hooke's law. This k is a constant of proportionality. So here are a couple of springs. We're going to start with spring 1 on the left. You'll notice the displacement is 0. We're at our natural spring length. This is the equilibrium point for the spring. But when we add a mass to the spring's going to move up and down. You'll see what happens as I let it go. Notice the different color vectors. We've got a key on the right side. Whoa! The green one is our velocity, the direction of our motion. The yellow one is the direction of the net acceleration. Then we have our individual forces. With gravity, what direction is gravity always pointing? And then we have our spring force, which is changing direction based on its compression. Remember that the spring force will always point back towards that natural length position, that equilibrium position. As we start moving through here, we can start calculating the spring constant. And here's what happens when I change that spring constant. Let's make it a larger spring constant. And you see that we have greatly reduced the amount of extension and compression. Spring constant is basically the springiness of the spring. If I add some damping, damping is an external force acting on the spring that's going to cause it to slow down a lot quicker. Right now I have my damping set to 0. I can also change the amount of gravity. And as I change the amount of gravity, for example on Jupiter, we see the gravity force vector, the weight force vector, is a lot larger than it was. On to drag force. Drag force is a type of fluid resistance that acts on an object through a fluid like air or water. Drag force opposes the motion of the object and depends on its shape, size, speed, and the properties of the fluid. So let's say you're driving down the highway. As you increase your speed, you're going to feel more air resistance pushing against your car. This is called drag force. The faster you go, the more drag force you experience. Shape and size of your car also affects the amount of drag force. Modern, sleek, and streamlined cars have less drag force on them than the bulky cars of the 70s and 80s because it has a less surface area facing the direction of motion. The density and viscosity of air is also going to influence the drag force. On a hot and humid day, the air is denser and more viscous than on a cold, dry day, so you're going to experience more drag force. Drag force has many applications in physics and engineering. For example, drag force is going to affect the flight of airplanes, rockets, projectiles. Engineers use aerodynamics to minimize drag force and maximize fuel efficiency. Drag force also plays a role in sports like cycling, skiing, and swimming. Athletes wear special suits, your tech suits. They may shave their arms or legs, and they normally wouldn't, but for an important race, reducing the amount of drag is going to give them an advantage. There's also swim caps, because hair is going to feel a lot more, catch a lot more drag force in the water. Helmets may also reduce drag force and increase speed. Drag force can also be used to slow objects down when you want them to slow down, like parachutes and brakes. Several equations for the drag force. First is the F sub d equals negative bv when the object is moving at low speeds and the fluid is viscous, like a marble dropped through honey. The next one is Fd equals negative bv squared when there's a high speed or the fluid is turbulent, like a skydiver falling in air. Finally, there's Fd equals 1/2 Ca rho v squared where C is the drag coefficient, rho is the density of the fluid, A is a cross-sectional area, and V is the speed of the object relative to the fluid. For us, no need to memorize. Whatever equation we should be using is going to be given to us. We can solve these types of problems using our force problem strategy. Identify the forces, draw a free body diagram, Newton's second law equation for each object, and solve for whatever. Let's go ahead and practice this. We've got a rubber ball of mass m dropped from a cliff. Ball falls, subject to air drag bv squared. Using a free body diagram, label all of the forces at some instant before it reaches terminal speed. Terminal speed is your ending speed. It's the final speed you will get to before you stop accelerating. So we're going to start with the easy force. Weight force, going down. You drop the rubber ball, it's going to instantly be in free fall. Eventually, though, there's this drag force that's going to act on it, Fd. And as more time goes by, that drag force is increasing and increasing until eventually your up force vector is going to equal your down, which means you have no net acceleration. We call that no net acceleration terminal velocity. So that's what your free body diagram is going to look like. State whether the magnitude of the acceleration of the ball of mass m is increasing, decreasing, or remaining the same. The acceleration is decreasing. Think about the stuff that makes it go minus stuff holding it back. If the stuff holding it back is growing larger and larger and larger until it's equal, then the net acceleration is going to be getting smaller and smaller and smaller. On a velocity versus time graph, this might look like square. Whoa, that's not a square root. Your acceleration is eventually going to be 0 at terminal velocity. I think I've rambled on enough. You can never solve too many of these types of problems. For more practice, there's your AI prompt. Use calculus, don't use calculus. Ask each other, ask me, and keep asking until you get it.